Ready?
Yep.
Welcome, EECS 16A. Woo!
Very
Take
good.
it away, my friend.
I will. I'm so excited.
I know.
Are you excited?
Well, don't be excited too much, because you know what happens when you get too excited. The internet.
I know. Okay. Arranging windows so that I can see chat and I can see you guys and I can see the camera. Very good. Okay. Let's get started. First, announcements. Good morning. The midterm grade is out, and you have an optional midterm redo, and that redo is due Monday 9th. In the same post that the grades are posted, you also have the instructions on how to do this redo if you want to, because it's optional.
But you only get Clover if you do the redo.
Oh yeah, is that right? Yep. I don't remember all the rules.
Yeah.
No,
so
my
no
time there was no
redo.
Clover. My time, you got the midterm, you got your grade. That's it. Okay.
Evolved. Now we care about not the student succeeding in exam, but actually succeeding.
Learning. Yeah, I know. It's much better. How does the redo work?
Well, just read the web page.
Yeah.
Read the web page.
Read the web page. Everything's explained there. Okay. So what else? Questions. So the average was, I think, 70.5 out of 90. That corresponds of about 75%. And as we said at the beginning of the semester, this class is not you get the grade that you get. It's not curved, which means that you are not competing with each other. Nobody's competing for an A or a B. You get an A or you get a B, which I really like. So in this bin definitions for grades that we have, this would be a B+. What do we have to say about that, Mickey?
What do we have to say?
I think it's pretty good, right? We're learning.
It's really good.
Yeah.
I think it's really good. We're pretty happy from how you did on the midterm overall.
Yeah.
Yeah.
Very good. Are we going to get the grade distribution? Why do we care about the grade distribution? We only care about the grade distribution if we want to know how somebody else is doing, right? All we care about is the average was 78%. We know what we did. We know where we are in the bin. That's all we need. That's all we care. If we're competing, then we want to know the distribution. We start doing analysis, start losing sleep over it. No point. Okay. Questions? Okay, the answers have not been released. That's right. Okay, I'm going to keep going because we have a lot to do today. Okay, last class. Last class, we looked at some tricks or some new techniques to do circuit analysis, which would help us taking something or a circuit diagram that might look a little scary and complicated, and making it easier, simpler, and easier to deal with. So we looked at superposition, which was a technique that we could use because our circuits are linear. And if we were given a circuit that had more than a voltage source, more than one voltage source or current source, we could actually solve the separate parts of the circuit by setting either the voltage source or the current source to 0, doing the analysis without the other sources, and then going back and summing all the results. Okay, I'm going to close my sun window here. Okay, better. So, okay, and then we said, okay, what we do in order to use the superposition, we set all the other independent sources that we have to 0. If we have a voltage source, then we will change that voltage source and replace that voltage source with a wire. Why can we do that? We can do that because we also learn about equivalence. And we know that...
Anna, just a note for next time. We shouldn't release the grades immediately before class. Maybe after class, because everybody's just looking at the grades. You know, folks, it's not going to help you looking at the grades right now. So better maybe just watch the class and then look at the grades.
Okay.
They're not going to change, I promise you.
They are adults, Mickey, and we would do the same. They will look at the grades and then they'll come back. Or some people are already coming back. Look, they're adults. I was talking about equivalence here. Okay.
Sorry,
but I agree with you. It was supposed to have been released last night. All right. Okay, voltage source. We can replace voltage source with a wire because we looked at equivalence. And what? Why is it true? Why can we replace a nulled or a zeroed voltage source with a wire? Anybody? Because they have the same IV relationship. Very good. They are equivalent. If we have a current source, then when we zeroed that current source, we replace that with an open circuit because they have the same IV relationship. And yes, their graphs are the same. Very good. And we do the analysis of our circuit. Okay, we compute everything and then we sum. We also looked at ways to simplify the circuits and find equivalent circuits when we have this zeroed voltage and current sources. And there were two things that we could do to find the equivalent circuit, which we looked at the Thevenin equivalent and the Norton equivalent. So to find the equivalent, we could analyze that circuit as with zeroed sources. And we know that we can zero the sources because our circuits are linear. And then we could either apply, what would we do here to find them? Let's see if you remember. We do a test, right, to that circuit to find the equivalent. And we were going to write the equivalent, let's say the R Thevenin as either a V test, V test over I test. We did this last class. If you didn't see it, please go back and watch the lecture. And there were two ways that we could do this, which was we could apply a voltage here, which we call V test. And when we apply the voltage, we would have I test. So we would apply a voltage and measure the current. And then we could determine what would be this resistor R Thevenin based on V test and I test. The other method that we could choose, and today we are going to do examples to see when it makes sense to apply a voltage or apply current. We could apply current, which we know it's an independent current source. So we would know I, I would be unknown for us. And then we can measure the V element here, which would be our test. And we saw that if we use this method, we would get pretty much the same relation, where we would find the R-Thevenin that would be related to this V-test and I-test. Okay, and those are the main tools that we learned in the last class. Today we are going to apply them over and over again. Wait, isn't current R Norton? Yes, yes. The equivalent circuit that we used with the current source and the resistor was called R Norton. And we also established that R Thevenin and R Norton are the same, which makes sense because we want to use these two methods to find an equivalent circuit. And that equivalent circuit was the same. Very good, very good. Good memory. All right, so let's do two practice examples and to make this a little bit clear. Hopefully very clear. Okay, I will give you this circuit, which you have seen before. I think you did this in discussion even yesterday, where I have two resistors, R1 and R2. And my goal here is simplify my life always. Why make it complicated? And we want to get to a circuit, an equivalent circuit that we would have a voltage source and a resistor here, where we were calling this R Thevenin, and here V Thevenin. Okay, so what would be the equivalent circuit for this? How could we find R Thevenin? We know from my little review here that what we are going to be looking for is to express R Thevenin as V test over I test, right? Okay, so let's do step by step, just to fix the method here. Don't take shortcuts. The shortcuts will get you at some point. So here's the circuits that I want to transform into an equivalent circuit. Pretty simple, and it's easier to learn things from simple things. Okay, so step one. What was the step one in our method to find an equivalent circuit? Well, step one was to find this box here, right? This box, which is a circuit with zeroed sources. Okay, look at this circuit. Do we have any sources here? No, no sources. So I'm just going to draw it again to label things so that we follow this method very well. We have here R1, R2, and we are applying the equivalent method here. So no sources, and we are going to measure here this open circuit, right? This is what we want to measure, either by applying a voltage or applying a current. Okay, so here I can already say, okay, my V open circuit is 0 because in my circuits there were no voltage sources. So I can say that V Thevenin is going to be 0, right? Correct? So first step's done because I gave you a very, very simple circuit. Now, what would be step 2? That's right. Finding the current. Yes, it's to apply either a current or a voltage and do the test, right? We're going to find V test and I test. So you can choose. Why is it 0? Because there is no voltage applied here. So there was a question there, why is VThevenin 0? So if I had to zero the sources, right? So because in the circuit that I gave you, there's no source, just for example, then there is no voltage there, okay? For now, but now we are going to do a test. So now when we apply a test, we are going to put a source for our test. So I will have resistor 1, resistor 2, and here I'm going to choose current source, which will be I test. So I will apply a current to do this test. And now let's do our analysis, right? Let's label our nodes. So I have, forgot to label R1 and R2. Let me complete here. R1, R2, I test. Okay, so remember that in our method, we had to introduce this element. So this is what I did here. Before we had an open circuit, no voltage across, right? Now we have this current here. We close the circuit and I'm applying I test. So since this is an element that I brought from the outside, I know that I'm going to have a voltage across here, and which I'll call V test. And this voltage is not the voltage of the element, right? This is the voltage that we are going to measure across that part where we had here our, when we had here our open circuit, okay? And then because I'm applying this I test, I'll have a current I test here. Over here, resistor 1, I'll have current. What current is going to be going here to resistor 2? Same current, right? And let's label the potentials now. So I'll have here, I'll have 0, my reference, and I'll label this potential here U1. I'll have, let's follow the passive sign convention. I'll have here VR1, and across resistor 2, I'll have VR2. And once we have labeled the circuits as we know, we can apply the rules that we learned so far, right? So let's apply first KVL. So if I want to go from here, 0 to U1, which is the circuits that I had to start with, right? 0 to U1, I have to go through voltage R2, voltage R1, all the way to U1. And I know that the voltage that I'm going to measure across here is what?
Oh, no, there's a question about a node between the resistors.
Yes, yes, there is a node between the resistors. I can label that for you. But we are not analyzing that node, right? What we want to analyze is what's the voltage across here? And what is the voltage that is across these 2 points here? That's right, that's going to be V test. So I can write that V test is going to be equal, doing KCL from here to there, right? To get V test. So V test is going to be equal what? Go from negative to positive, take 2 lifts to get to the top, VR2 plus VR1. Very good. So I'm going to write, it's going to be VR1 plus VR2, or VR2 plus VR1. Very good. Now, let's see what we know about these voltages. These elements are resistors. So we can apply the element definition of the resistor to find what VR1 and VR2 are. Ohm's law. Very good.
There's a few questions here about the passive sign conventions. If we do obey them
for
here
the
or
current.
not.
Thank you. I was expecting this this question. So passive sign convention, we have to obey here, right? For these elements, which we are. And then the question might be, okay, what about this current source? Well, current source has a set current, right? And the voltage V test that I'm measuring here is not a voltage in my current source. I'm measuring it between here, and it's that's why I set the element like this. As you remember, it's an independent current source. So it's a given, it's a fixed value, okay? The other currents are what we want to find out. All right. Yeah, thank you, Christian, for that question. I was actually expecting that to happen. And it's also a question in the homework. Okay, so let's see. I will write then VR1, which is the voltage across resistor 1 as IR1 plus then VR2, I'm going to write IR2. Somebody in the chat already went one step further, saying the currents are actually equal to I test. So indeed, we can write V test, in this case, is going to be I test R1 plus I test R2. Remember, what we wanted was to find a relation between R Thevenin, which would be V test over I test. Okay, so I'll write this V test over I test is equal .
Okay, there's somebody mentioned about breaking the rules and stuff about the
I will go back.
current sources.
Yeah. Let me just finish here. Okay, very good. R1 plus R2. Okay, so in this case, I found here that R Thevenin, in our case, is for this circuit is R1 plus R2. So I can go back here and say that R Thevenin equals R1 plus R2. Now I'll go back to the question there. Okay, when I do this test, the I test or V test, I am introducing a known value, right? I go to the lab and I decide that I'm going to put a current across that, okay? I'm not doing analysis in that element. I am just setting a current there and I'm saying, okay, this is my source, I'm going to put the currents there. And that's what I do here. So it's not part of the circuit analysis. It's an independent current source that I am adding here. And what I want to find out is what's happening inside this circuit. And remember when we build the matrix, we always build the matrix with the unknowns, which are in our circuit. And as a result, we found the knowns, which in this case, this I test. So I'm not breaking any rules here because I am setting this current, okay? And that's a separate thing from my circuit. And I am analyzing the circuit with that test to come to this relationship. And then how do I do this? Then I set my unknowns here, right? I said, okay, there is a current here. There is a current here that is set by my element, by that current source, external current source. So I have to obey that sign. So I know that current is coming this way, and I know that the current is coming this way. And then I went here and I said, okay, that means I have VR1 here, and I have VR2 here. Is that clear? The same thing would be for the voltage. You will take a voltage, you take a battery, and you're going to put the battery there, and you cannot change things in the battery. You cannot say, oh, let me just say it's positive and negative. But let's say we do. Let's say I changed things. It would be all negative and it would be all canceled out. Right? Is that clear? They are equivalent. Okay. Okay. Any other questions? Why did our voltage, why did voltage not work in this case? Well, I'll do an example where it makes more sense to do voltage. The next example will do voltage, okay? But, okay, you actually know the answer before I go there. What would happen? Let's think here together. What would happen if I have this circuit and then I decide to put a voltage here? What did we learn about this circuit? If I have a voltage across this circuit here, what would we have? Which circuit is that? That's our voltage divider. That means that the voltage across these resistors would not be the same, right? And that means that then we have two unknown currents here, and we have two unknown voltages. So if I set a current that is known, then I know that there is only one current going through this loop. So it's easier to analyze the circuit. And that's a very good question, because that is your decision, right? That's when you go to the lab and you decide to use this method to analyze your circuit. Now you should be able to answer, or it should be more clear to you what we do here in this next example. And hopefully this is an example that it will make you go, aha, I get it now. Okay. All right, so same problem. I have R1, I have R2, and I want to find what is the equivalent circuit such that I can represent the IV characteristics just like we represent the Thevenin equivalent. Okay. Here's Thevenin. Keep asking questions, okay? I don't mind the answer. Okay, step one. Step one of the analysis is what? Have a circuit with zeroed sources. Well, okay, I'm being easy on you, but we already have no sources, right? So step one, we can say, okay, sources are zeroed. In step one, we have V Thevenin or this V open circuit here equals 0. Okay, we've done it. Step one succeeded. What's step two? Step two now is when we have to decide things. When we go there and we pick an element, a physical element to do this test. What are we going to do? Can be a voltage source or a current source. Voltage source, pick the voltage source. Why? Why does it make sense to pick a voltage source? You know. Where did you see this? Oh, if I have a voltage across here and I have this and this node, what do we know about this? The voltage is the same. We learned in our touch screen, right? This is how we did the analysis of the touch screen. So we know that if we put a voltage across here, the potential across all these nodes, it doesn't matter how many we will have here, will be always the same. Remember? Okay. See, you have the skills you need to answer these questions. Okay, so let's do that. We are going to have R1, R2, And now I am going to add our voltage source, which I'll call V test. And I am going to have I test. All right. Shall we do the analysis?
Yeah, let's do it.
Let's do it. Okay. So here I have one current. I have one current here, which I'll call I2. And then I have a current here that I'll call I1. I will also write our VR2, VR1, obeying the rules. But we already know, right? We already know that VR1 is equal to VR2, which is equal to V test. Everybody with me? One yes. Yes. Two yeses. One. Thank you. Okay. More yeses. Now, what can we do here? What rule should we apply? It's always the same, right? Let's apply elements definitions. We have two elements in our circuits, two resistors. So what would we apply here? We'd apply, okay, Ohm's law for both. And by applying Ohm's law, we would get the currents. So I can write I1 equals Ohm's law, delayed, yes, very good. Okay, I1 is going to be equal V test over R1. And I2 is equal V test over R2. Clear? I just applied Ohm's law to these two elements here. And we established that R1, VR1, VR2 are equal to V test. So instead of writing VR1 and VR2 here, I just wrote V test and V test. Good? All right. Now, what other law can we apply here? We can apply KCL. So if I apply KCL, I can write that I test equals everybody agrees? I1 plus I2. I agree. Very good. I1 plus I2. Now, we already have an expression for I1 and R2 that takes into account V test, our voltage. So I will write that I test equals V test over R1 plus V test over R2. And what were we looking for? We were looking for an expression that would give us R Thevenin equals V test over I test. Right? So let's play around with this expression here. So we get to something that looks like that. So in that case, if I write, I'm sorry, V test over R test. Oh, sorry. V test over I test. I test is going to be equal 1 over 1 over 1 plus 1 over R2, which can be rewritten as R1, R2 over R1 plus R2. Okay, in mathematics, this is an operator. What is it called? This operator, R1 times R2, parallel operator. That's right. So let me, I will write our result here in pink since it's so important. Let's say R1 times R2, R1 plus R2, which is a parallel operator. Okay, with these two examples now, we have two definitions that we can use from now on. Jargon or shortcuts that we prove that they work. This one says that if you have two resistors in parallel, as you have here, because we know that the voltage potential is the same, then the equivalent circuit is the parallel operator for resistors in this case. And if you have two resistors in series, the equivalent resistor is the sum of the resistors. So that means that if you are given a circuit that has a bunch of resistors, either in series and parallel, you can simplify them by using these two equivalents, the R-Thevenin method here, and knowing that the sum of the resistors, you're going to use the sum of the resistors if they are in series, and you're going to use the parallel operator if they're in parallel. Okay, go ahead, Darren.
Hi, good morning, Professor. Really quickly, I think I just missed the part about where you explained that in this example too, the node potentials on the upper part and then node potential on the bottom part would be equal. Could you please go over that really quickly again? I didn't catch that the first time, so. Okay,
yeah. You can also go back to when we were doing our other circuits, especially the one for the screen, okay? But basically what we do, we call this node here 0, right? So we are going to say, okay, this node down here is 0. And then if we had to label all the nodes, I'll do up here, okay? So we have a resistor here. So that's one node. And then let me do the other node up here, right? This is all that we have. So if I label this one 0, and I label this one U1, and I want to measure the potential across here, then the potential is 0 minus U1, so the potential is always the same. And then what we did in lecture, in the past 2 lectures, was to have lots of resistors this way, right? And we saw that the potential across these nodes were always the same. Does that ring a bell now?
Yeah, it does. And this is because for R-Thevenin, we want to set the whole V element across the 0, right? So like U1.
We want to test, so it doesn't matter. This could be a much, much more complicated circuit. So we want to look at that as a black box, and we just want to measure what's out here, basically. And for here, we are setting a voltage, and then we find the current, or we find the relation, the voltage current relation.
Okay, all right, thanks for clarifying.
No problem. Okay, very good. So here it's some definitions for you. And with this, we kind of, we can go and start a new new thing here in our module. Now that we have, learned everything about resistors, practice those circuits until you get the intuition. My advice is if it's still difficult for you to see why I'm saying, oh, this is the same current, this is the same voltage, then be diligent, use the node voltage analysis, and you will always get to that answer. And then you will get to a point where you look at the circuit and say, oh, this is a voltage divider, this is that, and where can you practice? Oh, you can get practice problems, old midterms, old homeworks from the web. So there's infinite amounts that you can practice. So now in our next module, or in the next subject in this module, we are going to start looking at capacitive touch screens, which are the ones that we use, right? So so far we have been using this resistive touch screen, which are squishy. Don't see them that much. Maybe in
anymore.
Anymore. But first it was, yeah. But sometimes even when you go and you have to sign your credit card in stores, that's still resistive.
Yeah, that's true.
They're squishy, right? And some of them, most of them now have iPads. But these ones, right? This is hard. It's not squishy, and it turns out it gives us much better resolution. It has many pixels, and that's why we can write. Here I can give a lecture and write this beautiful handwriting here because of this capacitive touch screens. So because it's capacitive and we haven't talked about capacitors, before we even go and try to develop methods, Alex, we are not going to go do differential equations here. They stay in 16b. Here yep. We are going to stick with linear stuff. Okay. Anyway, because we are going to use capacitive, then we need to define capacitors. But before we define capacitors, I want to do a little science review here for you guys, because it's important that you understand what's we understand here. Okay, so first, science review. Periodic table of elements. Remember looking at, yes, Mickey.
Yeah, I just want to say about linearity. Capacitors are linear devices. It doesn't matter, even differential equation, but we're not going to look at transient state. We'll only look at steady state cases. And so we won't see these differential equations in this class, but we'll definitely see this in 16b.
Yeah, we'll assume that. I will explain when we get there. I'll explain. 16b. If you like differential equations, you will see in 16b. Okay.
Oh yeah.
All right. Periodic table of elements. Remember, you can find out lots and lots of details about elements if you look in the periodic table. And why do I care about elements here? Because I really want you guys, when you see a circuit element or a diagram, when I am writing here, resistor, and then a voltage source, and I don't know, a capacitor, I'm jumping here, I'm saying that one is a capacitor. I want you guys to know that in this wire is made of matter. It's made of materials. These elements are made of materials, and materials have electrons. They have valence electrons. They have a nucleus, and they have protons. Remember? So materials have charge. So when we are looking at charge and current, we are making the charge that is present in these materials move around. We are either getting all the charge in one place or all the charge away from that place, and so on. Think about that. It will help you understand capacitors. Okay, here there's some interesting things you can see. For example, the atomic number here of different elements. And then once you know the atomic number, oh, science, remember, you can also do some analysis of where those electrons are. So when you see these cool pictures of how an atom looks like, where you have the nucleus and you have these electrons moving around, well, in circuits, we make these electrons move in a very organized fashion. And when you have a material, you have millions and millions and millions of discharge, right? So we don't run out of electrons because the materials have discharges. Then in chemistry, probably in high school, you did this. I know that I had to do many times and sit there and go, okay, if this element is not 29, then I can do the distribution 1s2, 2s2, 2, remember? And all the orbitals. Oh, yes, exactly. No, they're not going to hunt you, but it's just for you to put in context here. So all these orbitals. And then there were orbitals at the end that were incomplete, right? Or we didn't have more things to put there, exactly. And those are the electrons that are just free to move around. It's easy to move them because they are not attached to anything energetically, right? We also had to do this, remember Pauli's exclusion principle? Remember where in one orbital, only 2 electrons can be there, spin up, spin down. And you would have to fill these boxes, spin up, spin down, and then, okay, analyze things in chemistry that way. Okay, we came to study computers. Yes, very good.
Well, computers are made of something.
That's right. Look at this. Yeah. We forget. Okay. Then now I will also give you a tiny little bit of solid state physics. Why? Because it matters. So solid state physics. When you learn that, which you are not going to learn in this class, except for these 2 minutes that I'm going to spend here, there are different materials that are used in all these electronic components that we're using here in our circuits. Some of them are conductors. We are not going to use semiconductors in this class, but if you're interested in semiconductors, you can take 130, 143, 134. What else? You'll learn semiconductors. 105. 105 has some introduction to semiconductors. In the circuit elements that we use here in 16A, we are going to use conductors and we are going to use insulators. Okay, so I want you to understand the difference, the electronic difference between these two materials. So if I have a conductor, our wires are made of conductors. That means that these wires are made of materials that present low resistance, remember? And that means that they have lots and lots and lots of electrons that are free to move. So all you need to know here is conductors have lots of electrons that are free to move. Free, they're not attached to anything, and many of them, okay? If we were to use semiconductors, semiconductors have lots of electrons too. They are materials. But in order for these electrons, to move, we need to give some energy for them to be in a state of energy where they can move. Okay. And once these electrons receive that energy, and that energy can be by applying a voltage across it, then that electron will leave that state and go to a place where it can move and contribute to current. And it's going to leave behind a space. So that space, it's a positive charge. And we call that space holes. So in electronics, the lack of electrons, meaning when electrons move, when we moved them from one place to the other, that means we left behind a positive charge. And that positive charge is called holes. And a hole carries a positive charge. Okay? We are going to look at positive charge and negative charge today. And then finally, insulators. Insulators are also called dielectric materials. Dielectric materials. And the difference between a semiconductor and an insulator is that the energy that you have to give for an electron to be free to contribute to current is much, much, much larger than the energy that you have to give to an electron in a semiconductor. While in a conductor, the electrons are already free. So if you find, is it possible to get charge through an insulator like this? Yeah, it is. Do you have your sparkles there, Miki?
No.
No, okay.
Yeah, I do actually. No, I do.
Yes, okay. So if you give enough energy, you can actually move electrons through an insulator. There you go. And that's what Miki is doing there, where he has a very high energy capacitor and 2 wires, and the 2 wires can break the air insulation, and you have these sparks. That's how we get storms also, right? Okay.
You know, the different materials are like the electrons are kind of like children. You know, conductors are like babies. You know, they wake up by themselves. You don't need to wake them up in bed, and they'll wake up all night. You know, just move around very easily. Then they grow up, and then then you have to ask like, hey, come on, wake up, wake up. You need a little bit, but then toddlers will just come out of bed. But then teenagers are pretty much the dielectric, because it's no matter what you do, they would never come out of bed till like 2 p.m. Right?
Yeah, that's a very good. Unless they are on Discord texting, then
yeah, that's true.
Then they wake up early. Okay. All right. So my students here, all 252 of you, or 250, and the ones that watch later. 2 things that I ask you. When you see an element in a circuit diagram, remember that element is made of materials. That means there's charge around. Okay, now it's our job to move that charge the way we want. Second thing that I beg you to remember, when you see a symbol like this, which is the ground, you will see that symbol as, okay, this is 0. This is my potential reference. This is not a wire where electrons can escape from. Why am I asking you this? Because I do get to upper division when people say, how come I don't run out of electrons going through the ground? So ground is 0, a reference for potential. Charges are everywhere in our circuit because of the materials. All right, now let's talk about capacitors. What are capacitors? So capacitor is a device that can store energy. And just as we are talking about independent sources of energy, we mostly use batteries. There were quite a few questions about current sources. Also, examples of current source, but capacitor is another voltage source. It can store charge. How are charge is stored in a capacitor, I'm going to explain. But for now, there are different ways of making a capacitor. You can find a capacitor that you have materials that are rolled like this. And the materials that form a capacitor are always conductors that are separated by a dielectric. What's a dielectric? A dielectric is an insulator. So that means that if you have a conductor here in this top plate, and you have a conductor down here in this bottom plate, and they are separated by a dielectric, that means that there should be no current going from one plate to the other, right? Because they are separate, unless you do something that allows that current to go through. Typically, capacitors come with some specifications. In your lab kit, you do have capacitors. You can go and try to recognize them. So you will see in a capacitor, for example, a voltage, and that is telling you what would be the maximum voltage that you can charge that capacitor to. I think Mickey has looked for different examples of capacitors for us.
I do. Yeah. Do you want me to show?
Yes.
Can I
And
share?
please. Oh, so I should stop sharing?
I don't know. Well, let's see if it works. Yeah, maybe you should stop just a second.
Okay.
Can you see that?
Yeah.
Okay, I got one capacitor here. Actually, I have a book of capacitors. So this is a book of capacitors. And you can see that they have a certain unit here, and it's filled with really, really tiny capacitors. And these are the units of the capacitor, and that's the rating that they have. These are called surface mount capacitors that you put on very small boards, and they're really actually tiny. I mean, I'm going to put one on my finger, and then you'll be able to see. I mean, this is really, yeah, this is how small these could be. And imagine just soldering those pretty
nightmare.
Requires some skills. Right. So we have other types of capacitors. These are ceramic. These are called ceramic capacitors. There's also a very small amount of capacitance, which we'll explain later what this actually means. But these are also quite a tiny one. Then we're starting getting to the larger ones. Here's an example of what's called electrolytic capacitor. And if you actually take a look, let's see if it has, yes, it has some rating. I don't know if it's possible to see. Can you see the rating?
Yep.
So this one is 10 volts and 470 microfarads.
Microfarads.
Right. And then, that's a bigger one. Oh, this is 1,000.
16 volts and 1,000 microfarads. Yes.
Yeah, that's right. And then I got this one.
Nice. Look at that, 80 volts.
That's 80 volts and
100,000
microfarads. And you know what? And that 80 volts, right? That's pretty big.
That's pretty amazing.
This one is actually pretty incredible too. This is 3 volts only. 3 volts, but it is 5 farads.
5 farads.
Now, 5 farads, that is a lot, because the other ones that I showed you were at the picofarad, 10 to the minus 12. This is 5. So this is, many orders of magnitude, billions orders of magnitude more than the small ones. Okay. All right.
Great.
Do you want to charge them?
You can charge them. I will start. I will first explain how charging works. How about that?
Okay. How about that? Yeah. Okay.
Yeah.
Sure.
Okay. So now I'll share. We are such a good team. Okay. Let's go to the physics of capacitors. I have to move here so I can still see the chat and you don't see gray boxes. All good? All right. Then everything is in place. Okay. How physics of capacitors. So let's see here. I have a capacitor. Here is my 2 plates. I already put electrons there because I want you guys to remember that the electrons are everywhere, right? in these materials that we have here. And in the middle here, we're going to have a dielectric material, which means that these electrons that are in the two plates cannot go through the dielectric. So there's no path through the plates to them. So what would happen here? Since I introduced the concept here of a switch, and the switch in my circuit here is open, nothing really can happen. So in this situation, what we have is we have metal, we have an insulator. I'm going to start calling the insulators dielectric because we learn. And in this case, nothing is happening because we need energy to move charges. Energy is needed to move charges. And right now, we don't have energy because we have a switch that's open. So things to remember: no current across the plates. Oh, how are we going to do circuit analysis, I wonder? And we need a voltage source. A voltage source is needed in order to move things, right? Is needed to move charge. Otherwise, nothing is going to happen here. But because I gave you the little speech about electrons, we know that there are electrons everywhere, right? Because this is made of materials. Okay, so how would we charge? What would happen to the capacitor? So once I close this switch, that means that now I have a voltage source here. This voltage source gives the energy that we need in order to move charges. So the charges that are here in my cable, in my voltage source, they now have a path to go to this capacitor plate. Well, the charges that were here in this capacitor plate, also the electrons that were here in this capacitor plate, now have a path to move around, right? So we have electrons moving all around here because now we close the path. So if I was looking at the system at time equals 0, nothing was happening. When I look here at a certain time after I closed the switch, I see current, which means that I have electrons moving that way. I have electrons moving that way. In this plate here, we have less electrons. And if we have less electrons, what do we have? We have holes. We start having positive charges. Okay. Then, okay, we keep going, and there is, the path is still there, and I keep putting a lot of electrons here. The electrons keep moving around. So at a T2 here, time 2, where this time 2 is larger than T1, okay? After this, I'll get to a point where I have negative charges in this bottom plate, and I have positive charges in the top plate. Okay, will that keep going and keep going and keep going? No, okay. At some point it will stop. When is that going to stop? When we run out of electrons? So when all the electrons are in the bottom plate, we never run out of electrons. When it stabilizes, that's right. when it stabilizes mud. Now let's think about what does it mean to stabilize? That means that, okay, we kept filling up this plate of with charges. And these charges had nowhere to go because we have this insulator here in the middle, so they cannot jump up there. And we kept all the charges that were in the top plate kept moving and accumulating in the bottom plate. While here, we start accumulating positive charge. So because we are accumulating positive charge here, so now I have positive, I have negative. What does that mean? That means that over here, I have a difference in potential. And difference in potential is voltage. So now I have a voltage across this. If you take device classes later on, you are going to see that here we have established an electric field in this capacitor. Electric field, because I have positive charges and negative charges, right? And this potential difference that we formed here, let me just write so you guys have here, we have a potential difference between the two plates. Okay, so when are the charges going to stop moving? They're going to start moving when there is no difference in potential between our voltage source and this potential difference here between the plates. Why? Well, because we need energy to move charge, and energy is the difference in voltage. Remember the derivative of voltage. So if we don't have a difference in potential, no more movement will happen, and we'll say, okay, these charges are stored in the capacitor. Okay, so that means that at that point, if I measure the voltage across this capacitor here and establish that it's the voltage across the voltage source that I was using to measure them, that means I can just come here, cut this capacitor out, and now I have an independent voltage source. So what was my time here? So here will be at T4. Now we have an independent energy source. Yeah. Okay. And because we have an independent energy source here, the voltage, we have charges that are stored here. And that means we can use it now. Yes, Mickey, do you have a demo to show us?
Yeah.
Okay,
right.
Go.
I'm gonna share.
Okay. Yeah.
Can I share?
Yes.
Okay. Can you stop share? Yeah, thanks. Okay. What? Hold on. Of course. Hold on. Share. Okay. There you go. All right. So what we have here is the capacitor. It's 1,000 microfarads, and I connected it to a voltage source. Right now, the voltage source is 0, and it's also connected to an ammeter. Right now, it's showing, you know, the fact that it's showing minus 0.05 is just the accuracy between the two, so they're pretty close. So don't worry about that. What I'm going to do now is I'm going to start ramping up the voltage, and we'll see. You'll be able to see the current, and you'll be able to see the voltage. And I'm just going to increase it. So let's see. There you go. Voltage is increasing. What's now the current fills up so fast you actually don't see it, but then it reaches a certain, the steady state, and basically there's no current anymore because it's an open circuit, right? Let's just go up to about 7 volts or so. Yeah.
Are you
about 7 volts?
Mm-hmm.
Yeah, we have 7 volts, right? Okay,
Great.
so now what I'm going to do, I'm going to disconnect the voltage source from the capacitor, and then we'll see what's going on. Okay, so
Yeah.
This is the current source, disconnected. Now I'm only connected to the ammeter.
Mm-hmm.
And there you go.
Oh, it's
Now,
reducing. How come?
Now, because it's reducing because I'm measuring it.
That's right.
Right? That's one of the reasons.
You have a
because I'm
path for
measuring
the
it.
charges. Very good.
That's right. Now I'm going to stop it. And what I'm going to do is I've prepared up front a circuit with an LED over here. And I'm going to try to actually drive the LED with this. It's not going to be a long time because it's not that much charge, but I'm going to try to do it nevertheless. So here's what I'm doing. And then one here, and then one. Oh, you see it light and then go away? Or it was too fast?
It's it got yeah.
It was too fast.
It got
So
locked.
let's just,
No, the screen froze.
Oh, of course it did. Exactly. Okay, so I'm going to do it with this capacitor because that's going to last for a very long time. This is 5 farads. So I'm going to reduce it to 3 volts now, just for the sake of it. And I'm going to charge it.
For the sake of the LED.
Yeah.
Mm-hmm.
Okay, so you see how the current actually now starts reducing because it's charging the capacitor, and at some point it will stop. Okay, it will take time to stop, but then it will stabilize around 2.7 volts. Now,
no voltage difference. Mm-hmm.
Now, I'm going to connect that to the circuit.
Yay, look at that.
And now we've got yourself an LED that's turned on for a very long time.
And quite bright,
wow.
huh?
Because 5 farads, it's quite a bit long, you know.
Very good.
So yeah. So actually, Anna, just for the sake of time, let's see how the capacitor charge. What do you think? If we just increase the charge?
No, let's do that in 2 minutes. Let me do, or you think we are going to run out of time? Go ahead, since you are there, and then then you give it back to me. Okay.
All right. So look, it's still on. Wow, that's a lot of charge going on there.
Mm-hmm.
All right. So what I'm going to do now is if we look at this, if we look at this capacitor, it has a 10 volt rating, right? Okay. Well.
Yeah.
Let's do this experiment where we connect this to a voltage source. Yep. So now it's connected to a voltage source, and you see there's you know, the voltage is constant. There's no current, and you know, I'm just gonna keep charging this this capacitor.
You're going to be pushing voltage. Okay.
Yeah, I'm going to push the voltage. So yeah, so now it has 10 volts on it. That's pretty cool, right?
Very cool.
All right, well, let's just keep going, huh?
Yeah.
I mean, yeah, we should just put more charge and more charge and more charge and more charge.
Because then we can keep the LED for longer. Oh my goodness.
All right, well, wow, what a mess.
Was that a 10 volts by any chance?
Oh yeah, that was more than 10 volts. And oh my God.
But what was the spec of the capacitor?
10 volts only.
Oh my goodness.
This is what happened to the capacitor. And you see actually the thing that was rolled in.
Right.
See the dielectric. This is like a paper-like dielectric.
Yeah, it's mylar.
This is the aluminum that forms the conductor inside. And yeah. So now all the magic smoke came out and the capacitor doesn't work anymore.
Yeah. Sadness.
Back to you, Anna.
Don't do that on your own, please.
Yeah, and you see what I have in my, you know, wearing?
Yes. Very good. I'm so glad you did that.
Thank you.
Thank you. Okay, so I'm sharing again. There we go. We had the live demo here, right? where Mickey explained everything that I wanted to explain in this slide, where we used this capacitor as an energy source to light up something until the charges have redistributed themselves again, such that there was no voltage across. So then the LED couldn't work in some cases. Okay, so, but as somebody said in the chat, we are here to learn about computers, not about physics and exploding things. So let's go back to computers. And in order for computers to understand everything that I explained to you here with physics, we need to define things so the computer understands. So let's define our new element, capacitor. Symbol of capacitor is this. Just like we did for resistors and wires and open circuits, we can define a V element for that capacitor, and we can define the current arriving at a plate in the element. And the symbol for that element will be C for capacitor. So we know that charge in an element is going to be given by C, which is the capacitance that we were reading there, times V element. Charge, we learn, is given in coulombs. Capacitance, as we saw in the examples that Mickey was giving to us, is farad. And voltage, we know it's volt. All right. We also know that current through an element is given, is the derivative of charge over time, right? It's the gradient of charge. That's how we defined current before. So in the capacitor, if we say, okay, the current going through the element capacitor is going to be the derivative of charge, when the derivative of charge, because we know that the derivative of charge is current, times the voltage times the capacitance. So let's write this as the derivative of the capacitance times the element over time. Okay. Now, as I said at the beginning, we are going to consider capacitance here as constant over time. If you go to more advanced classes in circuits and physics, you will see that that's actually not the case all the time. But for us, we assume that capacitance is constant. So if capacitance is constant, I can take the capacitance out of the derivative, and I'll see that the I element is going to be the derivative of voltage, the time derivative of voltage. So gradient of voltage over time, the change in voltage over time times the capacitance, okay? Once we defined these elements, we can now do the analysis the same way that we have been doing for resistors and capacitors, for resistors and wires. And we can also draw an IV relation where here I'm going to have I element, but here, instead of having voltage, we have to say, okay, is the change in voltage over time? Because we saw here through many demonstrations that if the voltage, there's no voltage difference, there is nothing happening, right? Okay, and how would the IV characteristics look in this case? How do you think? You can always say, oh, it's a line. We are only looking at linear things here. So you can really be smart here and say, oh, a line, very nice, a line. So it will be a line that goes through 0. But now the slope here will give us the capacitance of our capacitor. Okay. I guess we ran out of time. So from the next class, I will start with the definition of capacitance, and we are going to do lots of circuits with capacitors. Yeah, there was one question. There was somebody with the light. Oh, it's still going with the hands on. Do you want to ask your question here before we stop? I forgot the name. I thought it was Kelly or something. No? No questions?
Professor, is
Yes. Yes, Infoma.
There's office hours in the next.
Yes, we have office hours every time after lecture.
Okay, I'll ask.
Okay, great. All right. Thanks, everyone. Have a good rest of the week and weekend, and we will see you back here on Tuesday. Be good out there.
Bye, everyone.